Hello everyone, this is Devabrata and welcome to our channel Schrödinger's Cat. Whether you are a curious mind, a passionate learner or a seasoned scholar, I am thrilled to have you join us today. Basically, we will discuss today the most important topic, the condensed matter physics for the IIT JAM, JEST, TIFA and NET GATE purposes. And here basically we have the introduction part. We have covered here 6 topics: Meissner Effect, properties of superconductor, critical field, critical current, London penetration depth, coherence length, isotopic effect, type 1 and type 2 superconductors, BCS theory, Josephson current, thermodynamics of superconductivity. Our topic is today superconductivity on the chapter from condensed matter physics. Total number of questions are coming. The IIT JAM, this is the name here, the solid state physics, devices and electronics, and here the number of questions are coming that basically the 9 to 10. And in JEST exam there are no specific topic in that name, but somehow 1 or 2 questions are coming, JEST and TIFR also. And CSI and NET there are 5 questions in this topic, condensed matter physics. Basically it no name should be not EMT, CMP, mind it, condensed matter physics. And the GATE exam there would like 7 questions are coming in this topic. So the exam point of view from GATE, this is very important, and in superconductivity most hot topic, and or 1 or 2 questions are just come. So basically we have just go ahead our main part, that basically the Meissner effect. So basically we have done here some theoretical concepts and formula, and after we go through the examples coming in CSI and NET and IIT JAM exam purposes. Basically here we have for this topic that this one and the direction in the this one. This is for normal sphere for T greater than Tc. The another one is that this should bend here, and we finally this type of shape for the superconducting sphere at T less than Tc. This is for superconducting sphere, and this is for normal. And here coming that the Meissner and this effect, basically the exclusion of magnetic flux from the interior of a piece of superconducting material. As the material undergoes the transition to the superconducting phase is known as Meissner effect. We just block diagram here by for better understanding. We now go through the properties of superconductors. That the first one is basically that rho should be equal to m by n square tau, where m is the mass of the electron, n number of electron per unit volume, tau average collision time. And for critical field we have this formula Hc equal to H naught 1 minus T by Tc whole square, where Hc is critical field and H naught be the critical field at 0 Kelvin. Like that, Bc function of T is Bc 0 Bc 0 1 minus T by Tc whole square, and the critical current density, that Jc, be the 2 Hc by R, and the another one be the H equal to H naught e to the power minus x by lambda, where lambda t by lambda 0 whole square is equal to 1 minus T by Tc to the power 4 whole to the power minus 1, where lambda t and lambda 0 are the penetration depth at T Kelvin and 0 Kelvin. And we have the another equation, that superconducting electron density Ns be the N naught 1 minus N naught by Ns to the power 4, and lambda t be the lambda naught N naught by Ns to the power half, and this is here. And another one, that the graph should be like that, this here is T and this is Hc, this one, and it is for H naught and it is for Tc, this is normal state and this is superconducting state. And that here we also deduce the London equation is defined, that lambda is equal to m by mu naught ns square to the power half, and here we get lambda is proportional to root over m, where lambda is called the London penetration depth. London penetration depth. So basically we have here that the result, this one is T and this one is N naught, and another one for penetration depth it would be like that, this is lambda naught, here lambda, and that is T, and this one be the Tc. So now that we have the isotope effect, basically the isotope effect critical temperature is proportional to Q D is proportional to 1 by root m, and the graph would like that, this one ln m and this one ln Tc. And go ahead our next topic, that the type 1 and type 2 superconductors. For type 1 we just visualize here that this is our M and here is H. So this one and this. This is for normal and this is for superconducting state, and here be the HC type 1. And go on next for type 2, which basically such as that the here the linearly increases and this should be decrease like that. So basically this one is the age and this be the M, and this be that HC1 and HC2. This one is HC, that is the normal region. Here this normal region, and this be the vertex region. And here we just plot for rho. According to rho, we just give to plot that rho and h, this would become like that. And this is HC, critical magnetic field, and this one is normal state, and this one is superconducting state. And for type 2 it would like that, this one, where this be the HC2 and starting point HC1, and this is the vertex state. Here we vertex state, rho versus h. This is for type 1 and type 2. And go through our next topic here, that the BCS theory, that basically electron pairs in superconductor are bosons, and its radius would become like that, R naught is equal to H cross VF is divided by EB, where energy gap Eg of a superconductor at 0 Kelvin is given by the formula that Eg at 0 Kelvin 3.53. This is a numerical experimental value, kBTC, where Tc critical temperature of superconductor, and this is your experimental value. And here just ECG lattice vibration, a pair of free electron thus coupled through a phonon is called Cooper pair. And here we just take a small graphical representation. Here this one is T by E, and this one is Eg function of T by E at T equal to 0. This should be 1. This is like that. Now go through our next is Josephson junction. Basically that Josephson effect and tunneling, and we have the equations like that. Ij is equal to I max sine 4 pi e Vt by H, where Ij Josephson current and I max be the maximum Josephson current, and this should be the AC current produced. And we have give here in general form, when we just, and there are many applications that, like recently superconductor have found application in switching element called cyclones. And here we have the formula like just graphical represent here TC to T transition from CV. We just see that this one. So this is another and that is another. So this is basically superconductivity to normal state transitions. So next to go at our last topic discussions here, that thermodynamics of the superconductivity. So basically here we have in general CV is proportional to S is proportional to exponential minus A Tc by T, where that the reverse formula is given as Cs minus Cn is 4 H naught square by mu naught Tc, and we have another that del G half Hc square gives free energy change, and Cs minus Cn Tc be the Tc dHc dt whole square at temperature in critical constant, and this is called the Rutgers equations. And we have already discussed here the isotope effect, like critical temperature is proportional to m to the power minus half. This is important for the NAT type questions in theta d proportional to in gate exam minus half, and alpha be the del ln Tc by del ln m. We just plot this graph. Isotope effect coefficient, and we just deduce some other discussions here, that the basically the first London equation is del Js del T is equal to Ns square electric field by m, and the second London equation be the Carl Js minus Ns square by m magnetic field, basically mu naught Ns square by m h. And in Josephson current, here another one is that a current is observed across the Josephson junction with frequency omega q v naught by h cross, that would become 2 v naught by h cross. This is basically the frequency where we found in the Josephson junction, and I just write 3 important formulas here for your numerical question solution. We just go at our next topic. Bz s equal to Bz 0 e to the power minus x by lambda. Second one is lambda function of t to lambda 0 is basically 1 minus t to the power 4 by Tc to the power 4 to the power minus half. Last one is Ns is equal to n naught 1 minus T minus Tc to the power 4. This is our formula here, and I just conclude one thing is that here we just, for exam point of view, we just write some formula and summary of the topic and go through the problem section, because you should do problem in the entrance examinations, and after that we just, when we just got some time, and we just discuss the theory briefly, and for your better concepts here, and like here we just for numerical answer solution we will go through the problem number 1 coming in the TI for 2014. Basically here the question says that a solid sample has the property that when cooled below a certain temperature it expels any small applied magnetic field from within the material. Which one of the following best describe the sample in the cooled state? TIFR questions we just try to solve by the concept that here given that the sample expels the applied magnetic field from within the material. So in cooled state, the superconductivity, it shows the that each B internal should be 0. So basically mu naught H plus M should be 0 or H should be minus M, or we have chi, the magnetic susceptibility H minus M by H, and we just put here the value and got the result minus 1. That is chi magnetic susceptibility unity with negative sign. Chi is negative with unity, that is called its diamagnetic property. So our answer would be the diamagnetic. B should be the correct answer. So go ahead, our next questions coming in just 2020. Just 2020, that the penetration equation may be written as lambda square del square B, where lambda the penetration depth. What would be the value of Bx inside a superconducting plate perpendicular to the axis and of thickness delta, where Bx inside a superconducting plate perpendicular to the x-axis and of thickness delta, where Ba is the field outside the plate and parallel to it, and x equal to 0 is the plate. So we just find the value of Bx. We have to find. This is our questions in 5 marks. We should be very careful for mathematical interpolation and manipulation. Here we just do calculation for mathematics carefully. That here is a plate. This one is x equal to 0 and this one is delta by 2. Thickness delta. So delta by 2 is basically this one. So by these questions, here we get from here question number 1, that equation number 1, del square B would be B by lambda square. First one. So del square B equal to B by lambda square. So its solution B would be A exponential x by lambda plus constant A dash exponential minus x by lambda. This is equation number 1. Applying the condition. What is the condition? That in B equal to BA at x equal to delta by 2 and x equal to minus delta by 2. So BA would becomes BA is equal to A constant, put x delta by 2, so e to the power delta by 2 lambda here, and A dashed e to the power minus delta by 2 lambda, and also that BA should be A exponential minus delta by 2 lambda plus A dashed e to the power delta by 2 lambda. From this we get A should be A dashed. This is equation number 2. So now we just get the value of BA. BA would become A exponential delta by 2 lambda plus exponential minus delta by 2 lambda, and it would become A 2 cos hyperbolic delta by 2 lambda, and we should find the value of A, that A should become BA by 2 cos hyperbolic delta by 2 lambda. This is equation number 3. So putting equation 2 and 3, we just put 2 and 3 equation in equation number 1. So putting equation number 2 and 3 in 1, putting equation 2 and 3 in equation 1, we get that Bx would be BA cos hyperbolic x by lambda divided by cos hyperbolic delta by 2 lambda. This would be our answer. Bx equal to BA cos hyperbolic x by lambda by cos hyperbolic delta by 2 lambda. Go through our next problem coming in CSIR NET 2015, that a critical magnetic field of superconductor at temperature 4 Kelvin and 8 Kelvin are 11 milliampere meter and 5.5 milliampere meter respectively. The transition temperature is approximately what? So we just write the equation in our summary and theory section, that Hc function of t would become h naught 1 minus t by tc whole square. Let we just find that at t equal to t1, Hc t1 and t equal to t2, that Hc t would become Hc t2. So Hc t1, that is h naught, put this value 1 minus t1 by tc, and Hc2 temperature t2, basically h naught 1 minus tc by t2 by t2 by tc whole square, and we just divide here and get Hc t1 by Hc t2 would become 1 minus t1 by tc whole square 1 minus t2 by tc whole square. So given data, t1 is 4 Kelvin, t2 8 Kelvin, Hc t1 11, Hc t2 5.5. Put the numerical value here. We should find tc is basically the root over Hc t1 by Hc t2, t2 square minus t1 square by Hc t1 by Hc t2 minus 1, or basically put this value here, sorry, minus 1, put this value over, we get 2 8 whole square minus 4 whole square divided by 2 minus 1, put this value, we just get 10.6. so 10.6 Kelvin would be our answer. Question option B is correct. So go ahead our next questions. Question number 4 coming in GATE 2015. A solid material is found to have a temperature independent magnetic susceptibility chi equal to C. Which of this statement is correct? So basically here susceptibility chi equal to mu by mu naught minus 1. Susceptibility is defined as where mu is permeability in medium and mu naught in vacuum. For diamagnetic, we know mu less than mu naught, that imply chi less than 0, that is chi negative. For ferromagnetic material, mu greater than mu naught, that chi greater than 0, that is this should be positive. And for superconductor mu should be 0 and chi should be minus 1. So basically the option B, where C positive, the material is ferromagnetic, this would be our correct answer. Go ahead our next last questions, that question number 5 coming in GATE 2015, that which one of the following represent the electron occupy for an superconductor in its normal and superconducting state. Very important questions for representation. That I just say one thing, that in normal slide some below Fermi level and some in empty level, and if material convert into a superconductor, electron above the Fermi level make Cooper pair and they fall back below Fermi level as same energy released during Cooper pair formulation. That in normal state that these are fermions and the spin be half. So if the Fermi-Dirac statistics holds here, and we have the Fermi-Dirac distribution functions, that 1 by exponential E minus EF by KT plus 1. So at temperature T greater than 0, it would like that, this one. And for the another state, the superconducting state, that would like that the spin S is equal to 0 and this holds B distribution function Bose-Einstein distribution functions is applied here, and we have the distribution function like that, Fe 1 by exponential of E minus EF by KT, and that should be minus 1. So this graph at temperature T greater than 0 would like that, this one, Bose-Einstein distribution function. So basically we have the option B for normal state, like this should be hold at T equal to 0, sorry, t greater than 0, and for superconducting state this would be the graph. So I usually give some problems for better understanding to do in a homework for better practices. So let me just have 5 questions. You just pause this video and take a screenshot quickly. The first one is a conventional type of superconductor has a critical temperature of 4.7 Kelvin at 0 magnetic field and critical magnetic field of 0.3 Tesla at 0 Kelvin. The critical field in Tesla at 2 Kelvin. What would be the answer? Second one is GATE MSQ type question. So basically 1 or 2 answers should be the correct. These are 2, and the another one, here are 3 questions. That first one is a graph, the plot of specific heat versus temperature according to the superconductor transition temperature, which will be correct. And second one is GATE net type question, and third one is also coming in net. You just pause this video and take a screenshot. So basically we have motto that we just summarize these chapters, and after we just solve the standard problem coming in net, GATE, SET, JEST, TIFA, and also the GATE. And after that, by solving this standard question, you just try to solve another all over questions coming through it, and you just keep in mind this formula. And after that, I usually give homework for better practice and understanding. So last but not the least, contact, solve this homework, and if anyone needs this file of my YouTube lectures, that mail without hesitation, that cat Schrödinger's 1935@gmail.com. Thank you very much. Stay well and happy. Goodbye. Take care.